Okay, yeah. Moving forward now, so we're going to look at some of the concepts that we might have already done. Some might not have, but maybe should be helpful. Right. Okay, yeah, from the previous session, you might have talked about some of these things. So we're going to really be defining terms and then saying practically how they look like in terms of EVM ecosystem. But this applies, of course, to all the other chains, even those that are not EVM compatible. And later on, we'll be looking at them in particular as we get into the practical segments of program. So, first of all, what is an address? You might have already seen addresses, but you don't know what the standard is, how they look like, and how to identify them, even in a number of other different formats of codes that might look similar to addresses. So here, from the definition, it says an address is a unique identifier in chain account. It is used to send and receive transactions. So the cost is required, of course, when you're going to send transactions, which is called gas fees, and we're going to be seeing how gas fees is calculated. But maybe just to demonstrate it, what an address would actually look like. You guys can show you already looks like this, but I'm going to repeat it. I'm going to repeat it so that we can see it practically. So ideally an address would look something like this. If it's an EVM standard of an address, it would look something like here. Okay, so that's a transaction hash. It's a lot much longer than an address, so an address looks something like this. So in calculations, when you get to Solidity, this is exactly 20 bytes, rather 160 bytes, which is equivalent to, let me first do this. So yes, an address would look like this. So yes, it's 20 bytes, which is exactly 160 bits, and that is the standard of an address in the Ethereum chain. So I'm going to be putting practically everything here that I define on the other end, what it might look like in real life. Alright, so the other thing is a nonce. So I remember yesterday when I was talking about transaction hashes, I mentioned something called a nonce, and I'm sure you've come across it. So a nonce is, if you've been working with databases, there's something called a primary key. So a primary key is that specific field whose values represent uniquely every single entry into that specific database. Either it's a table or a query or whatever it is that you're trying to write. Typically a table. The primary key field will contain a specific identifier that separates that specific entry from all the other entries. So in the context of Web3, in the context of blockchains, there is something called a nonce that serves the same purpose. It's used for a lot much more than just being a number. So it's a number that represents transactions uniquely to a specific address. So if I had a number of transactions here, each transaction has a specific nonce. So that number, this number here, so for this specific transaction, it's 4572705. Now you will not find any other transaction executed by this address. So this is the address that initiated the transaction. So it has a name because it's a verified contract, and we shall look at what it means for a contract to be verified. So it's a verified contract and it has a name, but this is the actual contract address that you see under the name Titan Builder. So now that contract address initiated the transaction that ended up to be verified on the blockchain 5 minutes ago. And that transaction had a nonce. Actually, the full name, nonce is an acronym. Let me actually write it here. It's a number. That's what it means. So for every single address, there's a counter that generates random numbers, which can never repeat themselves for a specific account. And what that means is that there will never be a transaction with exactly the same details as another that has already existed before it, including having the same nonce as another transaction that existed before it. So the advantage of this is that you can have transactions that are uniquely identified, because when you put all these objects, these components together, you'll be able then to generate a transaction hash that uniquely identifies that specific transaction from that specific account. So you're not going to find any other transaction on Ethereum mainnet that has exactly this transaction hash. Every time you query Block Explorer Etherscan or any other EVM, any other Ethereum's Explorer, would be Block Scout, you will always find the transaction, rather this transaction hash representing that specific transaction. And you can verify this by checking this on another Explorer. So here's Block Scout. So one of the things that are uniquely different, that are unique for every transaction, is the nonce. Typically, the only thing that can really be because every other detail about this transaction will replicate itself in another transaction. And then it's possible for this very account to send money again to that account with exactly the same value. And the transaction fees could possibly be the same depending on the network activity, which of course would mean the gas price would be close to the same. And these other details, there's a likelihood that they could be the same, but the nonce can never be the same. Maybe the other thing that could not be the same is the block number. Actually, the block number in which the transaction was executed. But it's also possible that two transactions could be executed and they are mined in exactly the same block and they have very similar details. So if I wanted to check this very transaction hash on Ethereum mainnet, what would happen? When I check it out, it should exactly return the same transaction with exactly the same details, including the nonce. So that's the transaction hash, and I paste it in Block Scout. It should give me exactly the same details because these explorers are just interfaces that display the state of a specific blockchain. So in this case, both explorers are displaying the state of the Ethereum mainnet chain. When I look at this, you can see it's exactly the same transaction hash as this. And it was mined exactly in the same block, 12 minutes ago. And I just have to refresh this so I can have the same information. Scrolling down, I think the information is really the same. Maybe when I check more details, I should also see the nonce. Okay. You can see it still reached 12 minutes ago as well. And 4572705. Is that exactly the same nonce? 4572705. Yes, exactly the same information. So that means that this transaction hash uniquely represents that specific transaction all the time. One of the reasons why is because this nonce does never replicate itself for that specific account. So you might find this nonce on a different account, but not this account ever again. Okay, so that is it for a nonce and what it actually represents. It's just a number that uniquely represents a transaction for a specific address, as you can see here. So if you found the same nonce on a different account, the transaction hash can never be the same because the transaction hash is picked from all the information regarding that specific transaction, is what is used for generating that transaction hash. I think we looked at hashing. Yesterday we did a bit of hashing, where you pick a set of data. Someone has no question. Yes, sorry, I can't hear you clearly. Do you mind if you type? Do you mind if you type? I can't hear you clearly. Okay. Alright, as a wait on her on type, maybe let's go ahead. So, yeah, what is a smart contract? So, smart contract is simply self-executing is not very accurate, but it's a set of instructions that execute on a blockchain in an execution environment on chain. So, within a blockchain, specifically smart contract compatible blockchains, there's an execution environment where smart contracts, where pieces of code, where encoded instructions in code are executed. Things like transferring funds to across accounts or running custom logic in smart contracts is possible. And let me show you what a smart contract will typically look like if it is written in Solidity. So it is possible to see a smart contract piece of code. That is one of the things that is beautiful about Solidity. Everything is transparent, including the code for the protocols that you're going to use. So for instance, if you're going to use Uniswap, or let me see what protocol. Let me type something here. Uniswap may not be visible, but I can find the protocol. Okay, there is Uniswap here. What is my token? Uniswap V2. Let me take a look at this. It's a token. Let me filter. Okay, I'm looking for a protocol that I can actually check out. Whose code I can actually see. Okay, so good. So when this is the smart contract, how do I know? When I scroll down here, I can see a number of properties regarding that address. So smart contracts and externally owned accounts. Now the difference between a smart contract and an externally owned account, let me type it here. Is that this one contains custom logic running for executing instructions on chain. Then externally owned accounts only hold funds. So although there's an advancement of these accounts where we have an account that does both, It can be held in your wallet as an externally owned account, but it also has capabilities to handle custom logic. Those are called smart accounts, and we might look at them later. But a smart contract typically only runs custom logic. It has the capacity to hold funds, but it's not the kind of account that you can hold in your wallet for just holding funds. It is designed to be a program, and we'll see how we can do that later on. So an externally owned account is simply holds funds in your wallet. And these are the kinds of accounts that you have in your wallet, externally owned accounts. Smart contracts, on the other hand, are the kinds of accounts that link to the custom logic which you execute when interacting with blockchain protocols. So yes, I was looking at this specific protocol. You can actually see the source code right here. So it has 39 smart contracts, as you can see. You can see all the logic that defines this protocol right here. So if you wanted to verify if this smart contract is legitimate or there are certain things it doesn't do correctly, you can always verify it on your own, or you can do it in non-browser based frameworks like Foundry or Hardhat to verify how these smart contracts operate. So with frameworks like Hardhat and Foundry, you can test your smart contracts. Let me see if I could show you something here. So with Foundry, you can test smart contracts. So you'd have to pick all this logic, or maybe query it through your framework right here. Let's try to open up. And you'll be able to test everything that you'd love to test about this smart contract before you maybe interact with it, or even as a security auditor, trying to evaluate the security and safety of this protocol. So there's a number of bug bounties that always come when you actually do it. I don't know if we saw this. So this is the advantage with Web3 is that all the logic is usually open, and it's open for you to see and evaluate on your own. Because with frameworks like this, we found it strongly open. You'll be able to evaluate the security, the safety, the reliability of the protocol by just looking at its code and then using that very protocol to evaluate the security of that code. So with platforms like Communify, bug bounties are always put up for you to come up and test the smart contracts and then document your results and where you think there's an issue with the protocol. So I use it a lot myself, excuse me, when I'm looking at certain smart contracts and I'm trying to evaluate them in terms of security. And yeah, later on we're going to be building with Foundry and seeing how we can actually use it for smart contracts testing. So it doesn't look very, very different from most environments. It's really just a package-based framework. So you can import it, you can have it imported in your machine and be able to use it to do smart contracts testing. And also just trying to interact with smart contracts in a much more efficient way. So yes, this is what a smart contract would typically look like in Solidity. So this is Solidity. There's also another internally embedded language called Yui, which is a little bit more advanced, but we could also do it later on. So this is what a smart contract would look like. Okay, so Aaron is asking, why do we need a nonce, yet the hash number sorry, I got off here for a minute. Can you hear me? So yeah, Aaron is asking why do we need unknowns if the hash number is also just as unique? Okay, so let me practically define it here. So the hash is a fixed length string. I don't know if this was defined in one of the previous sessions. It's a fixed length string that represents an arbitrary number, an arbitrary amount of data. What that means is that no matter how much data you feed it, it will always return a string of exactly the same length. So how do we generate a hash? So if I had pieces of data, for instance, if this was transaction information, all this information, no matter how much it is, no matter how much it is, it will always generate a number or a code of exactly the same length. You can see, even when I continue to increase this in the amount of information in here, the length of the string never changes. So that is what is called a hash. It's a fixed length string that represents data irreversibly. What that means is that you cannot decode this hash to recreate the data from which it was derived. That is what hashing is. That's how hashing algorithms work. They are not irreversible. They work by a mechanism called logarithmic difficulty. What that means is that when you have a result from one operation, you cannot reverse engineer the parameters from that result. So now, if we have this hash, why then do we need unknowns? So this is the thing about unknowns. For instance, if I had a number here, let's imagine this with unknowns representing a transaction. For instance, if all of this was transaction information, if I change just a single character here, turn it to 2, you will notice that the hash changes so drastically. It's almost like I have changed almost every information. When I change this to a 4, it becomes a different hash. When I change this to a 2, it also becomes a different hash. When I change this to 1, it becomes a completely different hash. So, what a hash really is a digest or an irreversible compression of data that is derived from all the inputs from which that data, from all the inputs of that data. One of those inputs being the noise. Does it make sense now? So the noise is actually an input into the data block that is used to derive the hash. Why is the hash unique? Because the noise will always be unique. So even if all the information about the transaction are the same, because the noise is going to be unique, the hash will be unique. So the hash is the output that is derived from a combination of all the other transaction information along with the noise that defines that specific transaction from that specific address. Have I answered your question? Give me a thumbs up and let me know. So they are not interchangeable. One of them is an input from which the other is derived. Is one of the parameters of the input from which the other is derived. So the hash is the result, and the noise is one of the inputs from which the hash is derived. So when this is taken through a hashing algorithm, all these inputs, including the address from which the transaction was initiated, because noise is different for every transaction for every address. Yes, please.
Emma, like there is something I would like to understand. So meaning the nose is it's like a label. It's like a label, like let me say transaction.
So a transaction is identified by a number of things, but each transaction has a unique number, which is called a nonce. So the full form of nonce is number used only once. So you might call it a label, but I don't think that would be very accurate. So for purposes of understanding the concept, It's part of the unique labels of a transaction, yes, you might say that way. But it's just a number really. That will never be the same for that specific address. I hope that was clear. Does it make sense? Okay. So moving forward, I hope now we understand the difference between an address, a nonce, and a smart contract. So then a block is just a collection of transactions grouped together and added on the blockchain. So in this very, let's see what I can explain first. So there's a number of characters about a block that I would love for us to explain, but we're going to first start it really slow, then get into more complex components of what a block actually is and what it represents. So when you think about it, all the transactions that have happened in every specific instance are bundled together into a block. When I look down here, when I look at here rather, you can see there's a number of transactions here. So this is block 1, and its transactions include there's transaction that, then that transaction, then that transaction. So I suppose these are transaction hashes. Each of them are bundled into the block. A block is a combination of transactions that is identified by a block hash. And we're going to see what a block hash is. So just like you generate a hash for a transaction, you also generate a hash for a block, based on the transactions that are derived from it. So what that means is that if you change any information about that block, it invalidates the block and actually disconnects it from the rest of the chain. I think some of these things were covered in the session before this, but I've been session 3. So what ensures data integrity in a blockchain is that all this data is pegged onto hashes. So if all the information in this block has already been hashed, and a block header or block hash is generated for that block, even a single change on that block will make that block different. And here's what's interesting. So when you have a block, a number of transactions bundled together, its block hash becomes an input for the next block ahead of it. So that means the block hash of the previous transaction, along with the transactions of that specific block in which the block that we're trying to derive, are all bundled together as inputs to generate the block of that specific block. So that means that block 2 will always have a hash of block 1 as an input. So if you change any information in block 1, it would change the block hash of block 1. And what that means is that it will also change the block hash of block 2, because that means the block hash, rather if you disconnect, it will disconnect block 2 from block 1, because now the hash that it has doesn't refer to a block that actually exists in the chain. So that might be very complex, but I'm going to show you a depiction later on that demystifies it for us. So a block is just a combination of transactions along with a hash of the previous transaction that we see. So many other components, including the Merkle tree of the transaction, and we'll also explain what a Merkle tree is. But yeah, essentially think of it right now as just a combination of transactions, a collection of transactions that are bundled together and mined to be a part of the longest chain of that blockchain. Then the consensus mechanism is the method through which all the nodes, all the participants in that blockchain come to agreement about what transactions to accept, what blocks to accept, based on the rules that have already been predefined. And yeah, so a hash is a cryptographic fingerprint of a transaction. As we've seen it, every transaction has a transaction hash. So this is a cryptographic fingerprint. Why cryptographic? Because it goes through a hashing algorithm that encrypts all this information. Every information you see here about this specific transaction. It's encrypted into the transaction hash cryptographically and irreversibly. What that means is that from this hash, you cannot derive the input. You cannot derive the information about this transaction. And also, for the specific blockchain, rather for the specific block, when a hash is generated, it's irreversible. So that's exactly the same principle by which we derive addresses and public keys from the private key. It's irreversible in the sense that when you hash the private key to generate the public key, you cannot derive the private key from the public key that was derived from it. So it's like a one-way operation. You can only get the public key from the private key, but not the other way around. And that's the only concept that ensures security of our assets and security of our wallets. So the public keys can be used to receive funds, but only the private key can sign transactions, but you can't get the private key from the public key. And yeah, maybe later on we'll look at the elliptic curve and how these addresses are derived. And for basic understanding, that's what we could do. Understand the hash as just a cryptographic fingerprint over transaction, over block, and so many other things as we look at them. Yeah, then mining, the process of validating and adding transactions to the blockchain. So, when someone actually hears the word mining, they might assume it requires some kind of mechanical energy to, I don't know, maybe get some mineral from the ground, but it's really not. It's not really accurate in that regard. It's just the process of creating new blocks on a blockchain. So what would qualify it as mining, perhaps, is that there is always a block reward for the person that mines the blockchain, rather mines that specific block or adds a block to the blockchain. So that specific address then did that act of adding a block to the chain gets rewarded from the block fees and a number of other fees that we will see later on. So here, then a Mako tree is a structure that arranges transaction hashes efficiently for verification. So yesterday I looked at the Mako tree a little bit. Maybe I could demonstrate it here. I'm forgetting the tool I used yesterday for writing. If someone remembers it, you could leave me. Let me get a new computer. So later on, we're going to see how we can practically calculate gas fees. So we've looked at transaction hashes already. And to explain what a Mako tree is in relation to transaction hashes, this is what happens. So, for instance, if you had 4 transactions, as you can see them here, each of them has a transaction hash. So you generate transaction hashes for all those 4 transactions, and then combine the hashes of 2 transactions to generate another hash, and also the hashes of the second pair to generate another hash. And do this continuously until you come to the very top hash, which is called the Mako root. Now, in every specific block, there is a Mako tree that is generated for the transactions in that block. So if it has 10 hashes, rather 10 transactions, the Mako root of the Mako tree that represents all those transactions should have a verifiable mechanism that can tell you as a verifier that a specific transaction actually exists in the block. So if you have the Mako root, you can verify that specific transactions exist in that block if you know the transaction hash. So for instance, if I knew the Mako root of these 4 transactions, and then I have the transaction hash of one of these transactions, I can verify that this transaction actually exists in the block where this Mako root is a part of the components that are stored in that block. So we shall look at Mako roots and Mako tree verifications as well. That will be in later stages when we start looking at concepts and airdrops, but of course that will be infinity. Yes, what's your question, please? I hope I'm not moving too fast. You could type the question or maybe you need to speak. Come back to what the issue is. A Markov tree. So a Markov tree is a cryptographic representation of transactions. So for instance, if we had 4 transactions here, each of them would have a transaction hash, like we saw what a hash is. It's a cryptographic fingerprint of the transaction. So if we have 4 hashes of 4 transactions, we will pair the first 2 transactions to create a hash above them, and then the next pair until all the transactions are done to create hashes above them. Then the derived hashes of the original hashes of those transactions are also combined until we come to the very top, creating only a single hash. For these 2 transactions in this case, we will simply also combine them and then hash them using the hashing algorithm like the one we looked at to create a hash at the very top, which is called the Markov root. So this is the entire Markov tree, and these are all leaves. I think I have an picture here that actually looks beautiful. So this is how you can have. These are all transactions. Now the hashing algorithm in Solidity is this called H256. And let me see if I can show it to you how we use it. So especially if you're working with memory reallocation. Yes, Aaron. So a Markov root is a hash, but it's a hash that represents a number of things under it. So in this case, it represents a set of transactions, as you can see here. Now it's used for verifying existence of transactions in a specific block. Why this is important? Remember yesterday when we were looking at optimistic rollups and validity rollups? We were talking about fraud proofs and validity proofs. So usually what happens with fraud proofs is that you as a verifier, you have to verify and provide a proof that maybe a certain transaction is erroneous, or it doesn't belong to a certain block, or there are some things that are not correct about a certain transaction. So for you to do that, you need to have all the data regarding the transactions that were involved in that specific batch. Are you following, please? You can give me a thumbs up. So, why it's important for us to have a Markov root is that it compresses all the information of a certain transaction into its transaction hash. Okay? Now you have all the transaction hashes regarding that, preparing all the different transactions in a certain block. Now, if you want to verify if transaction A actually exists in block 262 something, instead of you having to go back to all the transaction information and having to verify if there's a transaction hash with that specific hash that you have within the block, you simply compare that transaction hash against the Markov root to verify then if that Markov root is derived from a combination of transactions which include the transaction hash that you have. So it creates a verification mechanism that is efficient, where you don't have to go through the process of capturing all the transaction data of all the transactions in a block, which by the way is much larger compared to the transaction hashes of those transactions. So it creates a mechanism that makes it much easier for you to verify the existence of certain transactions, because it compresses all the information into simply and simply the transaction hashes of those transactions. Does that make sense? So it's usually used for verification of the existence of transactions in a specific block, and also to enable tamper-proofing. That mapper root is also a parameter in generating a block hash. So when you're generating a block hash, you have parameters like the transaction hashes themselves, the transaction data, the block hash of the previous block, and the mapper root of the transactions involved that are collected within that transaction. So we're going to see a depiction that shows us how the hash is generated, and why it's important for all these things to enable integrity, data integrity for a specific block. Okay, so that's it about the block. Okay, moving forward, we looked at mining, we looked at UTXOs we haven't, but I'll explain UTXOs a little bit later because it's a different balances model from what I'm just talking today. Then rollups, we looked at rollups yesterday. Rollups are L2s or blockchain frameworks built on top of other L1s designed to enable scalability. So we're looking at how L2s actually scale Ethereum or Bitcoin. We looked at examples yesterday. So for those that weren't here, so L2s are just blockchains built on top of other blockchains, typically on Bitcoin or Ethereum. They are just designed to enable these underlying networks have capacity to accommodate an ever-increasing number of transactions. So for instance, if you had an increase in about 50% in the transactions running on Ethereum or Bitcoin, through these rollups, they would have the capacity to accommodate all those transactions, which makes Ethereum much efficient and reliable. Then log transactions is one of the mechanisms that rollups actually use, which allows them to accommodate all transaction information but keep it only for a very short time. So I won't get into very much detail like this because we're going to see it practically later on. What I would love to talk about now and have us do practically is calculation of gas fees and all the different denominations of currency in EVM, using the EVM standard. So there are exactly three major denominations of currency in the EVM. We have Ether, which usually represents the largest denomination. So this would be different for different chains. So it's Ether because when we talk about EVM compatibility, what we mean by that is that every blockchain that has that capability works just like Ethereum. So it's EVM compatible. That means it runs executions of smart contracts in an environment that is similar to the Ethereum virtual machine. That's what EVM compatibility means. So one of the things that comes with that is that they use exactly the same currency model as Ethereum. Although they might name their tokens different things, but they use exactly the same model. So why I call this Ether? Because Ether is a native currency for Ethereum. So if you came to other networks like Flare, for instance, the equivalent of Ether would be called FLR. So I think I actually deployed a contract today with displayed the information just like that. Let me do something here and display it for us. Hopefully my screen is visible. Just a minute. Okay, just give me a few seconds. I'm going to deploy a contract here on Flare Post which is a test network for Flare, and then show you how it displays these tokens. Maybe I'll also deploy one on Ethereum and then show you what the difference really is. So this is one of the frameworks that we'll be using for writing smart contracts and testing them. Okay. After this deploys, it's going to display something for us here. I think we could use so yeah, I have my private key important here, that's why you see it's yeah. So when you see what it reads here, it estimated amount required was this C2FLR. Now this is the equivalent of Ether on the Flare network, but it follows the same model like we're going to see and explain it later on. Okay, C2FLR, this would be the testnet, Flare testnet, or FLR and Flare mainnet. Okay, so the second denomination is what is called Way, and this one is usually used to calculate. This is the second. So they each have specific purposes. This one is for front-end display, for you to be able to read the numbers in a format that is not easy. So this is the second denomination. And this one is used for usually to display gas fees. Then the third is Way, which is actually the smallest denomination of currency. This one is used to represent funds when transferring them. So every time you see a transfer operation, the wallet would convert Way back into Ether for you to see on the front end, but really in the background, you only work with the smallest value of Ether, the smallest unit, the smallest denomination Way for you to transfer value, for you to transfer value across indices. Why we do this is because we want to ensure accuracy, and each of these values has a comparison between each other. So 1 Ether is exactly 1 times 10 power 9. So that represents power in code of Way. But then 1 Ether is also equivalent to 1 times 10 power 18 in terms of Way. So if I wanted to represent 1 Ether in Way, what would I do then? I would have 1 with 18 zeros after it. I don't know what that is. Is it a quadrillion? That will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8. That is 1 Ether in terms of Way. Now 1 Ether in terms of Way is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this is 1 Ether in terms of Way. See that? So this would be a very difficult number for you to read. Both numbers would be hard for you to read if you are going to use them as values you're going to display on your front end. But it's easier to read 1 Ether. Am I right? So now we're going to see how we can actually calculate this and why gas fees are used and how gas fees are calculated from this. So when we look at the transactions here, back to Etherscan, we can see, we can try to calculate. Let's start with this. You can see that Now the approximate gas price right now is 0.131 Gwei. See that? So how do we get the value of this in the equivalence of ether? There's a Gwei calculator you can always look at it. Maybe even calculate how much money we will be paying for deploying smart contracts if we want to deploy smart contracts at this amount of gas price right now. Let's look at a specific transaction perhaps. Let me get started with this. So if I wanted to calculate this and maybe convert it back to data, how would I do that? So I have 0.131 Gwei. When you come to the calculator, I don't know if my calculator will be able to handle these right numbers. I'm sure PowerShell will. So I can do PowerShell. So yes, we have 0.131 Gwei. So what would we do for us to convert it back to ether? Someone can give me an answer. Will we multiply or will we divide? Because Gwei is a smaller unit, it will be Gwei. Yes, we actually divide. So Gwei is a smaller unit, so for us to get the larger unit, we have to divide. So I'm going to divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the value it returns for me? That will be 0.1. A very, very small number when it comes to ether when I calculate it back in terms of ether. A very, very small number. So, am I correct? So this would be the value in terms of each. Because when you see a negative 10, then that means that the value is much, much smaller than it appears here. So this would be the value in here. How about in Gwei? Because it's a 0.131 in Gwei, let's also do this. What is 1 Gwei in terms of Gwei? 1 Gwei in terms of Gwei is 1. Is 10. We're following. So because a Gwei is in the middle between an ether and Gwei, when we convert a Gwei to Gwei, it is half the amount of 1 ether to Gwei. So that's exactly it. So that means this would be this and exactly the same number. And that is the amount in Gwei of the gas price that we're paying for us to be able to deploy this contract. Whatever it was. So I'm going to verify this by looking at just a single transaction, then calculate back and forth between ether and Gwei for Gwei to determine the gas price in terms of how much money we've spent in terms of dollars, of course. So look at the latest transaction. Here we have a transaction here. Someone was sending 0.08005, or maybe if my MetaMask would allow, I could do a transaction myself, and then so MetaMask is slightly heavy these days because I think they're making lots and lots of upgrades. But I'm going to do this on Sequoia. So usually what I do is instead of me having to send it to a wallet, I end up sending it through Foundry because it will be more efficient since these interfaces. It slows down usually for me when I'm working. It's okay. Then I have to Sequoia here. So, oh, I don't have any support here. Maybe I'll substitute it. Done. Okay, I'm going to get some support here. You can then send them across these accounts. That will take us a while. So let me just focus on this transaction here. So exactly what I was going to do will derive exactly this same kind of thing. The transaction sent from one address to another, which would be one of my addresses to the other, and I would send, and then the amount that I would send. So this was this amount, that's the value that was sent. Then this was the transaction fees. So I want us to calculate the transaction fees from this gas price and see if we come up to the same value. So based on this price of ETH right now, if we will come up to the same value. So we have this as our way, the amount we pay in gas. See that? Now I'm going to explain the difference between gas fees and gas price and gas itself. So you can see down here there's a lot to know about gas. You have to go through details about. There's gas fees and there's gas price. So you might be wondering what's really the difference. Okay, so I have these tokens in gray. Right? Gas fees in gray. I want to see if I can come back to this same value in dollars of ETH by using the conversion that we've already determined. So I'm converting gray. Okay, so I'm converting this amount of gray to ether perhaps. Let's see if we calculated this, it will give us the same result as we see here. So if this is my amount in gray and I multiply it by this, I get exactly the same result in gray. It reads 118,470.85. That's the amount we have in gray. Now I want to get the amount of ether from this amount in gray. So I would do this instead of me multiplying now, right? Because ether is a larger denomination. And this is exactly what I get, 1.19847085. These calculations are important, and I will let you know why. Because when the time comes and you are building applications, then you have to specify an amount that probably someone has to pay for a certain token, rather for a certain asset or to access a certain service. You need to understand this concept because it will actually reduce funds from someone's wallet based on the code that you actually wrote. So it's important to know the difference between ether and wave and gain. No matter what chain you're going to build on, as long as it's EVM compatible, the principle still stands. It's exactly the same. So later on when I'm building smart contracts and all may be integrated from any frameworks, I will demonstrate this concept more practically. But for now, let's try to understand the concept. So you can see it actually gave me exactly the same result in terms of ether. Okay, so now those are the three denominations in which currencies are displayed or represented in the EVM standard. So those are three. So if we're on Solana, for instance, the smallest unit is called an Armstrong. Now this is a digression I'm showing you, but it'll be very helpful later on if you want to do it on Solana. The smallest unit is called an Armstrong, and its smallest unit, instead of being 18 decimals, is 9 decimals, away from the largest unit, which is the soul. Okay, I think maybe we'll just look at Solana differently someday. So yeah, we have this now, and I want us to calculate the amount in dollars. Okay, so this is the amount in ETH. So if this is the value of a single unit of ETH, how then do we calculate the amount we have? No, this is not the amount of a single unit of ETH. This is the amount of the amount in ETH of the gas price. Right? So now how would the calculation be? Someone show me. Because 1 ETH, let me first put this in place. So the very first thing we know is that 1 ETH is an equivalent of how much in dollars according to the current price. This is the price on Etherscan. It could be different in the market right now because it keeps fluctuating. Copy this. So yes, this is the price of ETH in dollars right now. How about what? How about this? How will we do the calculation? So that's it. It's simply a multiplication because we should go back to this. But anyway, that's the calculation. You just multiply it by this, so you get the price now. So since these are actual numbers, we have to remove the dollar sign. Okay, this is quite a very, very small number. Let's see what value it put us. What is the amount in the gas that we have here? 0.00512. Maybe the price is now looking different, so that's why the result is different. But this is how you do the calculation. You have the amount of gas in ETH, and you are trying to get the value in dollars. Let's look at the price of ETH right now. Calculate the value of the amount that you will spend in terms of dollars for you to be able to determine the price of deploying a smart contract or doing a simple transaction. Okay, so now let's talk about these elements, these components, and why they're important. So gas is just the unit of measure of compute power that you use for you to execute transactions. Now, a transaction is not just any operation on the blockchain. So a transaction is a specific kind of operation that changes the state of a blockchain. So if I wanted to get to know the price, let me actually demonstrate this here. And going back to this because this is a theory, so I can bring it to something that is much easier for me to work with. You notice that when I was deploying the smart contract, I had to provide an RPC URL and then an account. So what it actually means in Foundry that the account is the private key that is going to sign the transaction of deploying the smart contract. How about if I just wanted to find out the chain ID? Maybe Brian is asking what time is the session ending. We should end in about 35 minutes or 40. Alright. So for instance, if I wanted to just find out the chain ID of a specific chain, I want you to notice something. I don't actually need an account for me to do that. So I want to find out the chain ID of this chain. And then I provide the RPC that represents that chain. I think RPC is not trustable. This should be sufficient for me to get the chain ID of that chain. You can see it returned the chain ID. When I was running this other transaction, it required me to enter a password. So that password will decrypt the file which has my private key, which would then sign the transaction, which would then deploy the smart contract. In this case, I didn't have to do anything. All I had to do was simply enter the RPC and the command to get the chain ID, then my chain ID right here. So this is flare testing. Now, I was trying to do that to demonstrate the difference between a transaction and a static call. So a static call is a kind of operation that just gets data from the blockchain. This was a static call. I was simply getting data from this specific blockchain. A transaction, on the other hand, is an operation that changes the state of the blockchain. So when I was deploying a contract, I was adding more information to the blockchain. Now that requires you to pay for gas. That requires you to sign using the account that is going to pay for the gas. Now gas is just a computational unit used to measure how much complete power you have used. So when you see gas here, when you see gas should be somewhere here. Okay, there's gas limit here, then gas used. Gas limit. So there's a limit. There can be a limit to how much gas you want to use for transaction. Okay. And in this case, we used 21,000 units of gas. That's the amount of complete power that we used to execute this transaction. But each of those units has a price, and it is measured in weight. Now you get the difference? So each of these units, these 21,000 units, has a price and it's measured in weight. Now I think I see where the mistake was when I was doing the calculation. I needed to multiply the gas price by the gas units that were used. That's what I did to do. So this would be the gas price. This would be the gas price. That means the amount in weight of a single gas unit. So that's the amount you would expend in your tokens measured in weight for you to carry out that transaction. But then you've used 21,000 units. So this is what the value would look like now. And this is what I would multiply with this value to get that right gas price. And you can see this is actually right value. 0.05, 11.1. That's what we actually have here. Okay, so now that makes sense. What gas price is and what gas is. So gas is the compute power, the measure of complete power that you use to calculate to execute a transaction. So a transaction is an operation that changes the state of the blockchain. Then SQL simply fetches information from the blockchain. You don't need to sign transactions with your wallet. Rather, to sign messages with your wallet. Yes. Yeah, what you see here. So usually there's some kind of gas limit that is set for transactions, and so there's a component. There's something about blockchain. It's called denial setups, and it is only disabled by this component. So what happens is, maybe I'm going to. So this does represent the gas that we used, but there's also a limit that is set for the transaction. You can actually modify it. So here we use the 100% of the gas limit of all the gas that was assigned to this transaction, maybe from the wallet or from the application itself, which you can always modify it. There are some transactions you'll see where you don't actually use 100%. Then let's just complete this. So gas fees like you've seen. A transaction that goes beyond the gas limit always reverts, does not complete. So that is the only way some of these attacks are handled and neutralized, because eventually if a transaction has to require more gas than normally required, it will just be reverted. That's why applications cannot run endlessly in the blockchain, because you must have the gas to accommodate the transaction. As soon as the gas is used up or is beyond the limit, the transaction just reverts. So there's a possibility that the transaction will require more than the limit of the gas that was set for that specific transaction. It will always revert. It doesn't continue. It doesn't complete. That's what happens. So yeah, now we know what gas is. We know what gas price is. Gas price is the amount of cryptocurrency a user is willing to pay per gas unit, typically measured in weight. So each of these 21,000 units is worth this amount in weight for you to use it. So you multiply to get the actual gas price. Multiply this by that to get the actual gas fees. Now moving forward, gas limit is the maximum amount a gas user is willing to pay to spend on a transaction. Yes, sir. So the purpose I'm using the word wheeling is because it's customizable. Even in your wallet, hopefully in your wallet can open and show you something. You were wondering why I was using the word wheeling to pay. So for instance, if I want to send tokens to one of my addresses here, one of my other addresses, and say I'm spending all my tokens. When I click continue, the next step is going to be for me to finalize the transaction by confirming it. But the other details about it, as you can see, I don't even have enough gas for this. But this is what happens when I click on this pen. You can see I can modify the amount of gas I'm willing to spend. The cost of it is that my transaction will take much longer for it to be in line. When you look at this, if I reduce the gas, the transaction will take 0.2 to 1 minute for it to be made. When I increase the gas, the transaction will take a much shorter time. Now, this might not make sense for you as a one-time user, but a person that is simply sending funds across accounts in a single time, in a single instance. But for someone that does trading, high-frequency trading, these seconds matter a lot in terms of what transactions are going to choose to do, what transactions are going to choose not to do. So for me to add priority to my transaction, I can always choose either to, I can even go to the advanced section and increase or reduce the amount of gas that I need for my transaction. So I could reduce this to 21,000 hours. What that means is that my transaction will take a little bit longer than it would for it to be mined or accepted into the blockchain. When I save this, because this may not be very significant in terms of how much time you actually wait, because seconds are really, really short. But for transactions that probably require a lot of work for the blockchain to execute, the time might go significant and exponentially significant, which also means that the gas price might have to be really high for you to let the transaction be mined much faster. So I can confirm this transaction, and these funds will be sent. So it is signed, and the funds are on their way, so the transaction is pending. Should be complete in a matter of seconds. Yeah, it's confirmed. So now these funds are on the other address that you sent it to. You can actually look at this transaction in the Block Explorer and then compare it to this one that we're already looking at. So meanwhile, as it loads, we know what gas limit is, then the base fee is the minimum fee required for a transaction to be included in the fee. So every block has a base fee. As you saw when I was trying to modify the gas fee, it told me the limit has to be 21,000. What that means is that if you go below that, there is no possibility of your transaction even being included in the fee, because that's the minimum gas fees that is accepted for you to allow it for a transaction to be accepted in your block at that specific time. Yeah, Ether will offset it, the native currency of the Ethereum blockchain, but based on the chain that you're going to be working with, it might have a different name, but it's really the same standard. In relationship to Way, it's the same standard for EVM chains. So when we deployed this method, there was Way there that I wanted us to convert back to the native token of Flare so that we could see how much it actually is. But yeah, I think now we get the concept. So this is on Security Snit, and you can see the gas price here. It's I think higher. Yeah, the gas price is much higher on Sequoia. The gas fees is that, and this being the gas price, that means each unit of these 21,000 gas units is worth this price for you to run transactions. And you can see gas price keeps changing based on the network activity and a number of other parameters. So yes, that's the difference between gas price, gas limit, gas fees. I hope there is clarity there up to this point. If someone has any questions, you can as well raise your hand and go through it in detail. Perhaps something I didn't clarify. What causes fluctuation of gas fees is network activity. Because the more transactions a main pool has. So the main pool is where those transactions go before they are picked up to be put in blocks. The more transactions the blockchain has to verify at a specific instance, the higher the competition for compute power. So it's an economic model that simply creates an incentive for those that are willing to pay more for their transactions to be included in the blocks. So the economic incentive is actually similar to the simple economic cycle. Economics as we know, it's supply and demand. What that means would be that there's a lower supply in compute power. So if you're willing to pay more for it, then your transactions are likely to be included before others. So in the same sense, the value of that asset, which is compute power, now starts to rise. Now starts to rise based on the activity in that period. So that now only those that are able to make the price have their transactions included in time for that specific period. That's why gas price fluctuates. Depends on network activity predominantly. Yeah, I think we had an example here. So what we were trying to do here is converting ETH to Way. So we had 0.25 ETH, then multiplied it by 1 billion, which is the amount in Way. And this is what we have in Way. You can actually verify it now. So if we had 0.125 ETH and multiply it by 1 billion, which is equivalent to ETH of Way, so this will give us the equivalent of Way of this amount of ETH, which is that. You can see that is it. Or if I multiply this by 1, here is this. It should be understood and it should be. And for our shell, I think it's correct. So let me just do it manually. So it will be 0.125 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7. Now that is the amount weight of that value. You can see it's a very large number. It's not a number that you would easily be able to read. So now every time you're going to transfer funds, you're going to represent those funds in terms of weight because it's the smallest, most accurate value denomination in the EVM standard. So the wallets or even front-end frameworks, like we were looking at VM the other time, you can convert it back to Ether for ease of display. But really in the background, you're working with weight. So you must really know how to convert those values so that you always reduce the correct amount from the user wallets, or send the correct amounts to wherever you're trying to send value. And this is most typical even in smart contracts, because when you're writing them, there are going to be times when you're writing code that sends value across accounts. So you must know how much money you need to be sending. If you can find a smart contract here that has that component. Anyway, we'll look at it when we start looking at smart contracts. And, so we'll be writing smart contracts in Solidity language. And there's a number of things that we'll look at when we start writing smart contracts, including how to transfer funds, how to control logic, and how practically you can interact with smart contracts even with your wallets. So up to this point, if you have any questions, you can say, so we can clarify whatever has been left out. So we can go ahead. So there is no definite classification of transactions that will go over the gas limit that was set by the developer or by the wallet by default, but just the number of the amount of gas it will require for it to use depends on how many computations it requires. For instance, if a simple transaction like this was already sending funds, right? We used 21,000 units. So this probably was the limit of the wallet, 21,000 units of gas for transactions. So if I had a transaction that was sending funds to 20 people at the same time, to 20 addresses at the same time, that would definitely require a lot of compute power. A lot more compute power than it requires for this transaction. Probably 20 times more, I presume. That would require more than 21,000 gas units. But if the wallet limits it to 21,000, that means that transaction will be backed. Unless if I go back and modify the gas limit, like I was doing in my wallet here. I can always go back and modify the gas limit before I send the transaction, like this. So it's really about how much compute power the transaction is likely to use. Because what typically happens before a transaction is executed, there is something called a dry run. The EVM goes through the transaction, and the logic it's going to execute and estimates the amount of gas it's going to use. So sometimes it will even warn you if you're on a framework like Remix, tell you this transaction is likely to fail. Though it's not very clear sometimes why, but one of the reasons is that the amount of gas required for that transaction to execute successfully might be higher than the limit that was set by the NERSC or by your unit. So it's not that there's a classification, but it really depends on the amount of complete power that is likely to be used in the transaction. And when we start looking at solidity, we'll see how we can optimize our transactions for gas so that they could use less amount of gas than they would if we were to code in a certain way or were to code in another way. But also to maybe split operations across transactions so that we can control the amount of gas that is probably likely to be used by the execution of those transactions. Okay, is there any other question? If there isn't, I would love to close it here. And, if there's anything I left out, you can always look at it in the other sessions, but I think this should be the very last session looking at fundamentals. These are concepts that we're going to carry along into development. So if there's a concept you haven't quite got your head wrapped around, you can always go back to the recordings. So, they're actually all uploaded except for the previous two. Yeah, but you can always find them on the Decentralized YouTube channel. You can always go back to it at convenience. So hopefully today was helpful, and I wish you all a lovely evening.